Oh yeah, it's gonna be a good one.
So we came to a deduction that the reason everybody sits on that side of the class is because you go to that side of the class first.
I do? Okay. Sorry.
No, we don't care.
All right.
But
I like that honesty. We'd rather not see you that much, Jeff. So just go over there.
it wasn't a bad or positive don't care. It's just an observation.
Well, I like it. It was a deadly.
But maybe you only go to that side of the class because everybody sits on that side.
Because that's where all the hands shoot up. You guys are a little more subtly in need of help. They are very blatantly.
Maybe that's because they're stupid.
They just don't have them soon. They get the quiz because they know they're going to need that.
What's your question? I haven't even answered it yet. Yeah, I know. We'll say number 2.
All right, guys. I'm going to show this. I'll show you why it's important for you to show yourself the factoring step on this, because it's going to help you out when you get to the point when you're trying to figure out what does this thing look like. Because don't forget, whenever we get x-intercepts, we know how they act through those intercepts based on the multiplicity of the roots. Hopefully when I say all those words, hopefully we're used to what those words mean. Based on, did it come from like an x minus 1 squared? In which case, what would it do at 1? Would it go through or would it touch if it was x minus 1 squared? It would touch. It's like a parabola then. It's an even power. It's going to touch it. Whereas opposed to if I had x minus 1, for example, what would it do through 1?
Go through it.
It would go through. It's like a line then. It's any first power, any odd power is going to go through. So if I factor the top here, I should end up here. So make that equal to 0, I get x equal to 1 and negative 1. Those both have multiplicity 1. It should go through each of those roots. So just because we learn new stuff about asymptotes and all that stuff, it doesn't change what we knew before. That's still true. How it acts at zeros is still going to be the same. I can still tell if it goes through, if it touches. That all comes in handy. Y-intercept. Set x equal to 0. So the y-intercept would be 1/2. So if you want to be practical, you get those intercepts. Cool. Don't mix that up with the asymptote. All right? This is an actual y value of a point. The asymptote equation is an equation of a line. You with me? Okay. So where do the vertical asymptotes come from?
The domain.
The domain. So notice the x-intercepts are always worried about the top of a rational expression. Because that's the only way to make a fraction 0 is to make the top 0. And the vertical asymptotes are all about where does the domain have problems? Where do I have to set up walls that say, don't come here? So that's why he's always looking at the bottom. Okay. So how do you factor this?
X plus 3, x minus 2.
Good. So then you get your vertical asymptotes will be negative 3 and 2. So in this case, these are equations of lines. That's where you're going to graph those dotted lines. Well, the best way in that case. What about horizontal asymptote?
Ratio. I got 3.
Ha! Which case am I in? 1, 2, or 3?
2.
I'm in the second case where the powers are the same.
Yeah.
So then the shortcut is it's just the ratio of those coefficients, right? So horizontal asymptote is going to be y equal to 3. So if this would have been an x cubed here on the bottom, what would the horizontal asymptote have been?
0.
It would have been x cubed. It would have been 0. The bottom would have overwhelmed the top. It would have gotten larger quicker than the top, so the whole thing would go to 0. Cool. Of course, the other way around, we haven't talked about that yet. Slant asymptote is in our future yet.
Would you just repeat the C? Find the
So we're in this case where the powers are the same. Right? Therefore, the horizontal asymptote is going to be the ratio of the coefficients. maybe. And if you were to do long division here, the first step would be this goes into this 3 times, plus some remainder term that would go to 0. So that's why it's 3. It's got to go to 3. Okay, cool. Maybe. And let me show you this because this comes up in later classes too. And I don't know if you're going to like this or not. Part of me doesn't care because they'll give me another way to look at it. Here's the way this is traditionally done. What's the highest power in this whole thing? X squared. So if I divide top and bottom by x squared. You kind of with me? I can do that assuming x is not 0, but there we go. So if I divide top and bottom by x squared, what do I get? I get 3 minus 3 over x squared. With me? So I'm dividing it by x squared. 1 plus 1 over x minus 6 over x squared. Stay with me now. Don't give up. I should have said what I said because this is kind of nice. You can kind of see it a lot more directly here. When x gets really, really big, what pieces of this go to 0? So as x gets really big, doesn't this go to 0? And this goes to 0, and this goes to 0. So what's the only piece left alive when x gets really big? 3 over what? 3. So when x gets really, really big, the contribution of this other stuff doesn't matter. It's so small, it's going to be 3. What's the most important piece of the top? 3x squared. When x is 20, minus 3 looks like nothing, right? If I got $1 billion and I drop $1, I'm not going to be scrambling like I do now. Whereas on the bottom, what's the highest power? X squared.
Sorry.
You don't want me to dance, okay? So when x gets really big, how important are x minus 6? How important is that? Not. When x is 1 billion squared kills the hell out of 1 billion. So when x gets really big, these parts don't matter. So wouldn't that reduce to 3? So that's really what this is saying right here, just more directly. When x gets really big, these parts don't matter. They pale in comparison to these parts. That's why it's only 3 at the end. Okay. See, now you have 3 different ways to look at it. You've got the long division way, which I figured that most of us would kind of bypass. You've got the 3 possibilities. That's the way I stick with. That's the way to teach it. And you got this traditional way of doing things. Both the long division and this kind of explain why the little shortcut 3 thing works. So that's what I would keep in mind. It's important for you to know why it works. Okay. And finally now we can graph this thing. So what do we know here? The x-intercepts are -1 and 1. The y-intercept is 1/2. There's a horizontal asymptote where? 3. And where are the vertical asymptotes? Yeah, 2 and -3. Okay. So I don't want you to look at this like a whole bunch of like, oh my God. You see what this does? It breaks it down into how many places. 1, 2, 3. Wait, 1, 2, 3 kind of main regions. You with me? And what could it be doing on this side? It could be either up here or down here. Now, without doing any real work, why can it not be here?
There's no x-intercept.
There's no doors through the x-axis here, right? They're all over there. There's no way through the x-axis here. So I'll bet you anything it's up here. And just to double check, when you plug in a -4, oh, thank you. Save a little time. So 7.5. So at -4, it's going to be at 7.5. So it's sort of like this then. You guys with me? So I'll be kind of specific on a test. If I want like a real rough sketch, you can use something like, well, it can't be down there. It's got to be up there. There's no x-intercepts. Bam. Or I'll say plot several points and make it more, and then you've got to plug in -4 and really see where it is. You guys with me? Now, this should now be not that big of a deal. What must it do at each of the intercepts? It must go through. So it has to look like that. Yeah. So eventually it's going to get closer to that asymptote. How can you verify that? You can plug in -2. You can plug in 1.5. And make sure that it is down here. You with me?
Yeah.
Pretend to be with me. Make me feel good. No, don't do that. If you're not with me, let me know. But that's where you don't want to lose what we've talked about before. The whole idea of touching and going through made that a lot quicker than it could have been. I really don't feel like plugging 1.5 in there, even with my calculator. Yeah.
Where are you plugging the 1.5?
You plug it in where? To the function. You want to see where the function is. Yeah. Yeah. And finally, the same reasoning over here. Where must this be? Up here or down there? Up here. And just to make sure, I can plug in 3. F of 3 is, oh man, 24 over 12, 6, 4. Yeah. So 3, 4 is right there. So there's confirmation that it is up there. If I can go further with going. So these are kind of nice. These walls kind of tell me what the shape is going to be. I can plug in a point to see exactly like where it is in that little box. So it's got to be in this little box. I plug in a point, I see exactly where in that box it is. And the idea of the intercepts telling me where it can and can't go through narrows down the options for where it could be. So if I just needed a really rough sketch, that would be crazy quick. We can get that really quick. Very little work involved. Is my hope, where it will be eventually. So is there any questions on that? You can't quite go home yet, so. Actually, you can go home any damn time you want to, tell you honestly. Or you might stick around. You want to break the sequel? All right. You just got to get into that section and try it out. I want to talk about slant asymptotes real quick, and then I want a little preview of chapter 4. Kind of see what you guys already know. Here, let me do this. If you have your graphic calculator still, plot this in your graphic calculator. Let me see what form is on. So let me see, let me put this up here. What do you have to be careful about when you have a rational expression you're trying to put into the calculator? Yeah, the calculator cannot see that bar. That's what tells us, the humans, that's what tells us there's a top and a bottom. But exactly what I just did is what we need to do for the calculator. We have to tell it there's a top divided by a bottom. So if you leave out one of those parentheses, you've got an entirely different function. What's that? Oh, you get invalid? I like it.
I got like the. Yeah, I did too.
So let's see what it looks like. I got some funky ass window. I like it. So watch this. Everybody try this. Hit zoom. Do that. My least favorite thing. Let's see it. It worked well the other day. Zoom fit. Funky. Alright. Now see, this is what I hate about zoom fit. What's kind of crappy about this picture is, do I really need to see all this? Alright, so let's go in there and make the window. Let's make Y max just a little less than 230. Let's make it like 40. Let's see if that does good enough here. How are you doing? Can you guys see that? All right, so here we go. Let me help you guys out. Go to your window. Make it negative 10 to 10. Make the Y min, let's make it negative 30. And the Y max 40. Just like this. Does it say a go to? Oh. Hit second Y equals. Nobody else worry about this. And you see the one that says plots off? Yeah. Number 4, I think. Select that one. Hit enter a couple times. Now go to graph. Holy crap. Okay. Is everybody cool with the window? You with me? So it should look like this. All right. So hang on to that. What do you get when you long divide this thing? Yeah, x times this is x squared plus 3x. Change the signs.
I would explain why.
You guys with me?
Yeah. 3.
Negative 3. So negative 3x minus 9. Change the signs. You get this remainder term. This remainder term, of course, will go to.
There we go.
So if I'm talking about horizontal asymptotes, I'm letting x get really big. When x gets really big, 5 divided by big is all hell is small.
That's not it.
0. So what should our asymptote look like then? X minus 3. It's kind of nifty if you think about it. And look, doesn't it? Look at this. Doesn't it look like a straight line here? If I watch this. Put in there, hit y equals. Stay with me now. Hit y equals, go to y2. And we can plug in two things at once. Plug in x minus 3.
Whoa. That's crazy.
Now, if I could make that dotted, and I actually could, but I'm not going to. If I made that dotted, that would be the asymptote. Did we just prove it mathematically? So, exactly what I say on your handout, if the top power is higher than the bottom, it is going to go to infinity. And then if the top power is bigger than the bottom, doesn't the top grow faster? So it's going to grow unchecked. It's going to go to infinity. But it's going to go to infinity following a certain slant asymptote, a certain line. Yes, sir?
Some random line. I got the same thing as you did, but I got.
Oh, you got like a heartbeat. Oh, okay, I understand. Sometimes it'll put in there the asymptote. Where's their vertical asymptote for this guy? At negative 3. So for some reason it's
Yeah,
so some of you guys at negative 3, you might have a line strapping down. So it looks like a heartbeat. It does that sometimes when it can't resolve. It's doing up here and then it goes, oh, the next point's down there. Let me connect them. Some of us don't have that. Okay. Okay. Are you guys? What do you guys? You guys see slant asymptotes is that last option. So if the bottom power is higher, it goes to what? If the bottom power is higher than the top, goes to 0. If the powers are the same, the ratio of the coefficients, and if the top power is higher, Too bad, you got to do long division. And then you're going to put your dotted line exactly like x minus 3. That's how you draw it.
So it's whatever the answer is without the remainder, basically.
Exactly. So the remainder would go to 0. The remainder is always going to be over that x plus whatever.
Yeah, so it's just, like I said, the first part of that.
So when I go to graph this thing, was the x minus 3? I put my dotted line. Here's minus 3, that's the y-intercept, right? And then it's up 1 over 1, up 1 over 1. So you just put your little dotted line like that. And you've also got on top of that, you've got the vertical asymptote here, right? So do you see how right down here, now the scale is such that we can see this better, but do you see how that's living right down in here? That piece? Right here? So it's down here. And why should it be down there? Are there any intercepts up here? Where are the intercepts? 2 and negative 2. And see this, there's your negative 2. And there's your 2. So it still cuts it into regions. It's just now pizza regions instead of rectangular regions, right? It's triangular regions. Same idea. Oh yeah.
Numerator is a higher power. Whenever the numerator is
Exactly. So this little box on this piece of paper, they also have a box in the book too. Little boxes that designate these 3 possibilities. Top power higher, bottom power higher, power's the same. Those are the only things that can happen.
How do we determine the...
Oh. What's the domain? What's not the domain? X can't be negative 3. That's where the roll wants to go.
Oh,
When the power is higher on top, you always do long division.
Exactly, because then you can see the slant asymptote. Cool.
and so if it's quadratic, that's when we factor the bottom, but if not, we just go straight.
Yeah, I don't need to factor this because I can see the parts. It's just when there's more than one part to it, when it's a higher power on the X, then I have to break it down.
Okay.
Yeah. That's it for today because I gotta run and fix something up. So I will see you next time, and I'll have the quiz graded, and I'll have the next practice test. There you go. This is for real. Then it is just a constant function of degree. Whereas this is x minus 3. So here I know the top is higher than the bottom. I know I'm going to have a slant. The powers are the same. I don't have a constant. Yeah, that's great. This is going to be a true horizontal asymptote if the powers are the same. If the top power is higher, I'm going to get the slant. That's really that. Just putting it from because the top power is higher than the bottom, you get the slant. Then it'll be 0. If it's the same power, it'll be somewhere else than 0. It'll still be a flat line. So this whole thing over here is trying to find horizontal asymptote. So that's always letting x get 1 0. So the remainder is always going to be something over a higher power. So when x is really big, when you're doing this process, you can basically just say whatever the remainder is. So far, yeah. Because the bigger x gets, the more it's going to have to, and you can see that graph. The bigger x gets, the closer it gets to that line.
Yeah, it's one of the ones. Okay.
Just because that's always in the background when we're doing this process. So whenever the top power. Yeah. It's bigger than the bottom. Even if I had, now here's where it gets tricky. I used to, yeah. So I'm in power is less than the top side. So I have to long divide.
Later, guys.
And then it just square times, right?
That'll probably pay me more than.
Square, change the sign.
I can give you some ideas.
Square,
Thank you.
minus 7x.
Appreciate that. I'll help
Now
you.
For a dollar idea.
Whoops.
For another breakfast burrito.
Minus
Yeah,
7.
that's what I was gonna say. Yeah, that's what
No.
we said.
Plus 3x. And then I get 3x squared. Plus 6x, change the signs. So now it's minus 13. And then blah, blah, blah. And then I have a plus remainder. So this is going to go to 0. So now here's the funky thing about this. I mean, and I don't know why I picked the funky example to show you. I end up with a parabola. So if I graph that parabola, whatever it's going to be, itself is going to be in that square. It's going to go. So if you're trying to graph that and you calculate it, you're going to see at the end, because it really only matters when x gets really big, positive or negative. In the middle, it can do whatever it wants to. But it's going to have like a shape maybe like this and do something. And then at the ends, it's got to be following that parabola. So what we did over there, we did one that's a little less freaky.
Yeah.
X squared minus 4x plus 2 over x minus 7. So I know I'm in a situation where I've got a long divide.
Long divide, yeah.
Times x. Change the signs. 3x plus 2, so plus 3. 3x minus 21. Change the signs. And this almost doesn't matter.
Yeah, it doesn't matter.
It's going to go to 0. So that's right.
Yeah.
So the graph of this has got to eventually, let me see, follow this line. So how could it do that? It could kind of do, it could do like this, come down and over like that. It could come. So where's there for this guy? Where's the? Oh, what's that? It's 7. 1, 2, 3, 4, 5, 6, 7. So here's the vertical asymptote, right? Let's do 2, 4, 6. So right here's the vertical asymptote. Is that cool?
Yeah.
So then you can kind of see, this is what I'm talking about, and this is why people need to understand. It's pretty much always going to be something like that. It's just going to be this shape moved around. So you're going to have at least one vertical asymptote and then the slant. So it could either be some weird ass thing like this, or it could be like this.
But it's always
So how
gonna
do you
be
tell
this
which one
shape.
it is? You plug something in, right? Like you plug a 0 in. If I plug a 0 in, I get negative 2/7. It's down here, so it must be where it's coming up. It's either coming up like that, right, where it's able, and that's probably what it's doing. So it can come back here and approach this.
Yeah.
So at the ends, it's sort of like end behavior. That's what I should have said earlier. Horizontal asymptotes is very much like end behavior. At the end, I don't care what you're doing here, you better eventually start coming closer to that. So over here, it could be in here, or it could be down here.
So you figure
So
out
again,
what
you just plug in something, and if you get up here, then it's going to look like this, because it's got to be approaching that vertical, and it's got to be approaching that horizontal.
So just screw it. Plug in 8.
Yeah, just plug in 8, and let's see. So 64 minus 32 plus 2 is 34 over 1, so 34. So we're definitely way the hell up in there, right?
Yeah.
And then it is going to be like that.
Okay.
Yeah.
That's it. Okay, cool. So but it's always gonna be in that little.
So instead of having these box regions, where, and we see that like right there. Just imagine me taking that and moving it up. So what's this going to have to do? Going to have to kind of like.
Have to do a little
Yeah.
weird shape, right?
Exactly.
Okay.
So it's just kind of moving that wall, and he goes, oh shit, and he kind of starts curving up.
Okay.
It's exactly the same idea.
Alright, just slant. Alright, cool.
Exactly.
Fine. Thanks. Sure.
Just wanted to know for the slant length, this is slope, right?
Slope 1, and the
Right.
y-intercept 3. So that is just a straight up.
Isn't that the slope of the slant line?
Well, this is the equation of the slant line. So it's mx plus 2.
Oh.
Yeah, so it's
So
nothing
the-
more than
so
that.
also the slope
This
is
is
1.
the equation I'm
Oh.
graphing, and then it is linear in this case, so I can look at it down 3, like I think I was doing. I lost it. But down 3, and then I go up on it, and then I can make my little flat line. Yeah.
Oh, okay. And they can never really be like the 3 like horizontal, slant, and vertical. Asymptote.
No,
There has to be
yeah.
vertical and horizontal.
You can't have a
vertical
combination.
And slant, right?
Yeah, slant means you're in a situation where you don't have a horizontal.
Oh.
So horizontal means you can't have a slant. So they can't have a slant and a horizontal.
Yeah,
There are
but
some funky functions where you can have two horizontal. Yeah. Because it might be doing something different in the negatives as it is in the positives.
But they can't really be all three of the same.
No.
They have to be vertical with either one, right?
Yeah, you can always have vertical. And
Can't
then you
always
either have
have-
horizontal or you have slant. You
Okay.
can have both, yeah.
And like you said, those are possibilities, right?
Oh, what we drew up here?
Yeah.
Or,
Or just
um,
in the shaded region, because there's, or is it, or is that the final one that really has?
This
yeah.
one is, that's what it's gonna look like.
Yeah, there you go.
Yeah. I could, and then what I was doing earlier was it could have been here. And we really knew it wasn't there because there is no x-intercept here.
Yeah, it was able through it.
Yeah.
Yeah. Okay. That's just like we did in the graph. It's just gonna look all weird like that, like and then wow.
Yeah, so the slant really is not different. It's just, instead of being like this, it's just that.
Well, no, I mean like in general, the shape of these graphs is gonna have that gap. Like that.
Oh yeah, I know what you mean.
Yeah, like we did in the graph, like it was like that, and then it goes like that.
Exactly, yeah.
It's gonna have the gap instead of the regular, straight up.
Exactly. Yeah.
Okay.
Can't do that.
Thank you.
No problem.